বুড়ানিলে তো আর ওগুলি কথা কইতে পারবো না। এই যে বাচ্চাগুলি না, বাচ্চাগুলি তাইছে কইলে ফেলো, তারপরে কোশ্চেন আমি এখন কোশ্চেন করি। এরকম করি বুড়ো হচ্ছে। এখন হাঁটতে পারে? ওয়াকিং স্টিক ওই যে ওয়াকার ছাড়া?
কে? হ্যাঁ শোভিক, হ্যাঁ তুমি ওইটা ইয়াকে দিয়েছো না, ওই মনিরুল তাদের?
হ্যাঁ হ্যাঁ দিয়েছি, সবাইকে দিয়েছি। I'm unable to open my video. I mean the camera.
ওকে, ও তো
Okay, okay, okay.
no, তোমার your background is inverted, left parity inversion is there, left to right. No, Tunu's background, the poster. হ্যাঁ ওইটা, এটা parity inversion হয়ে গেছে, লেফট রাইটে চলে গেছে, y axis এর রাউন্ডে। ও আচ্ছা, না না ঠিক আছে, বোঝা যায় না বোধ হয়। বোধ হয় উল্টা উল্টে লাগে।
Okay, so in today's presentation, Otunu is going to present the slides, and I'm going to talk about. Yeah, okay, okay. So let me know when to start. I'm ready.
Yeah, just wait for 5
Yeah,
minutes.
okay, okay, okay.
And let your friends in, then we shall start.
Someone is trying to join. I mean, Biplab Ghosh. Yes. Yeah, Biplab. Okay. Abhijit Mondal has joined. Okay. Dr. Biplab Ghosh has 2 accounts. Yeah. Okay. I think my invitees have joined because Manurul Ali, probably his mobile is coming switched off. Probably he is unavailable. Okay. Anybody else wants to join? I mean, from your side?
Only Rubayan is expected. Huh?
Okay.
Rubayan, Orindam, and Ojoy.
Okay. Okay.
Other three. Rubayan from Spain, he is supposed to join. Because he has attended all these meetings.
Hmm.
Streaming has started, right? Okay.
Make it full screen. I mean, now, yeah, I can see it. Others, if others can see it or not, I don't know. বিপ্লব দা দেখতে পাচ্ছ তো স্লাইড?
It's okay. Clearly visible.
It's okay, full screen. It's okay.
Yeah. It's absolutely fine. We are okay. It's okay.
Yeah.
অতনু, which you are streaming, যেটা স্ট্রিমিং করছো সেটাতে ইয়ে হচ্ছে না, ওই ফুল স্ক্রিন দেখাচ্ছে না ইউটিউবটাতে। ও আচ্ছা, এই জন্য। ঠিক আছে, ঠিক আছে, ঠিক। ওকে। No. So it is beyond our. Okay.
Okay, good evening. Thank you so much for this kind introduction. And first of all, I am very glad and I'm honored to be invited by CASILab to give a lecture on my research topic. And also, I'm very happy that my research collaborators, Dr. Abhijit Mondal and Dr. Biplab Ghosh and Dr. Anushri Bhattacharjee, they are also present. Okay, and to cheer me up. And today's day is also very special for me, not for me, but for all of us who are doing research in quantum mechanics, because most of all probably do not know, most of us probably do not know that today is the 15th March, is death anniversary of Arthur Holly Compton, and whose research on particle nature of electromagnetic wave is for this work he got his PhD, sorry, his Nobel Prize in the year 1927. So today his death anniversary, and yesterday 14th March was Einstein's birth anniversary. So in these two auspicious days back to back, I'm here. I'm glad to. I'm very much delighted to give my lectures on this particular topic. And since the treat is from my side, okay, so I have to present the menu card first. So for all the participants present, I must say that there are total 59 slides here, so you have to have some patience, and I'll go very slowly. And I can see that most of us, those people who have joined here in this particular meeting, they are quantum mechanics specialists, so they will not find any difficulties in understanding things. But still, I'll go, since it is also being broadcast live in YouTube, I'll go very slowly and try to make things clear for all of you. So my today's talk title is Bipartite Mixed States from the Perspective of Coherent and Incoherent Basis. Bipartite means two-party system, because this entire work of us is based on two-party system, two-qubit system. Mixed state is something which I mean, is often appears in a system, because quantum in quantum mechanical system cannot be in pure state in nature. It always subjected to noise, and it becomes mixed. And coherent basis means you can say that entangled basis is a kind of coherent basis, and incoherent basis is a kind of synonymous to separable basis. So I'm going to discuss bipartite mixed states from perspective of two different types of basis. One is the computational basis, and another is called the entangled basis. So with this, I'm going to start my delivery of my talk. So please go to the next slide. Our research is actually based on a paper which was published in the year 2023 in International Journal of Quantum Information. The paper's title was Exploring Quantum Properties of Bipartite Mixed States under Coherent and Incoherent Basis. And in this paper, I worked with Professor Monirul Ali, Chandrasekhar Radhakrishnan, Anushri Bhattacharjee, who is there, and Biplab Ghosh was also also a author in that particular paper. And as you can see, my title was not much deviated from the paper title. So just keep the parity. I have maintained this balance by putting the title title of the talk same as, more or less similar to the title of the paper. Please go to the next slide. So first of all, the motivation of the paper that came to us was due to another paper which was published in the year 2022, is from Quantum Information Processing Journal, whose reference is given below in the footnote. In that paper, one of my previous colleagues from my earlier PhD days, he and his students, they actually showed that, which I have written in blue color, that for any general 2-qubit density matrix rho, L1 norm, which is a measure of coherence, is always greater than or equal to concurrence of that density matrix, measure of quantum entanglement. Now, this coherence, this entanglement, all these terms I'm going to explain in today's talk. This is my job to perform. So I'm just giving the motivation. That was the motivation of their paper, which was published in Quantum Information Processing Journal. So, in mathematics, so one thing is there, if you want to prove something, then you have to go for rigorous maths to prove that particular result. And if you want to disprove something, you have to give a counter example. So our paper of that was published in IGQI, on which my particular talk is based on, is basically a counter example to their statement of the paper. So they said that for any general 2-qubit density matrix, the L1 norm is always greater than or equal to concurrence. But one thing which they did not put emphasis on was the basis. Okay, so they actually perform these, but they actually proved that system from the perspective of computational basis, but they forgot to make sure that whether it is happening in incoherent basis, or whether to compare this particular statement in both the basis such as coherent and incoherent basis. It's because this notion of coherence is actually, when we measure the coherence using any particular measure, I mean formula, then this measure, all the measure of coherence are actually basis dependent. So if you change the basis, then the value of the coherence keeps changing. So in that particular paper, they did not shed light on that. So actually, you can see in the slide below, I have marked red a particular line that when we use an entangled basis like Bell basis, this inequality they are actually talking about is not holding. So that was the motivation of the work. Please go to the next slide. And also you see that some of the points, bullet points I have marked in blue, some other motivations are also there. For a complete knowledge of the quantum states, it is imperative to have a holistic view of qualitative nature of these states. So we want to actually also wanted to study that, okay, fine. So that the quantum information processing paper was not giving emphasis on basis. They were stick to computational basis only. But okay, we will also go for some other investigations, such as we will construct some states which will give the counter example for their statement, counter example to their proofs. And we will also study not only the concurrence and coherence of those constructed states, we will study their usefulness in teleporting unknown qubit from Alice to Bob. And we will also study the teleportation fidelity of those states, etc. And also in quantum mechanics, everybody knows that Bell inequality violation plays a very important and significant role. So to give a holistic view of the entire thing, we have studied not only coherence in our paper, but also the concurrence and teleportation fidelity and Bell inequality violation, everything that has been covered in our 2022-23 published research paper of World Scientific. So all these things I'm going to explain one after another in upcoming slides. Go to the slide number 5. Now, quantum coherence is a phenomenon which arises from superposition principle, and it also gives the total quantumness of the system, and it is a basis-dependent quantity. So, as I have already told you, that if you change the basis, the coherence value keeps on changing. I will show you how it actually happened in our case in the upcoming slides. Go to the slide number 6. And coherence in quantum mechanics can be also understood by the famous Schrödinger cat's experiment. Coherence is actually is a kind of concept which is behind the wave nature of light and the quantum nature of physics, as I have mentioned on the slide on the right hand side of this particular figure. Now, this particular figure that I have shown here is that of Schrödinger cat. So it says, everybody knows that Schrödinger cat is a theoretical example where is a thought example, thought experiment by Schrödinger, whose actual motive was to tell that in quantum physics, once until and unless you measure something, you will not be able to tell what state the particular system is in. And the given figure that I've shown you, that has been generated by the AI, artificial intelligence Gemini. So I wrote their Schrodinger's cat several times, and this figure that that was shown to you, that was being shown to you, that I liked most, and therefore I have implemented it in my particular slide. And in quantum mechanics, Schrodinger cat, which is the coherent superposition of macroscopically incompatible situation, everybody, all of us know that it means that in macro system it is actually not happening. In a macro system, everything is in either in zero state or in one state, switch on or switch off mode. But in micro system, we have qubits. So in between 0 and 1, there are infinitely many possibilities that a particular state can be in. And if you measure, I mean, you see the last line that is written, when the coherence of the superposition vanish, all quantum features disappear and replaced by just classical like ignorance of the cat state. It means that when you measure something in quantum mechanics, then the quantumness of the system breaks down, and you get the cat either as dead or as alive. Okay, go to the next slide. So quantum mechanics, there are two important things that there. One is the quantum coherence itself, which is the focus of our today's study, and quantum entanglement also. These are the two manifestations which is coming out of the linear superposition principle of quantum mechanics. Quantum coherence is a common necessary condition for both entanglement and other type of quantum correlations. By other type of quantum correlations, I mean such as quantum discord is there, which I have not studied over here. So everybody, all of us who are participating in this today's seminar, they must know that quantum entanglement is not only the type of correlations that we study in quantum mechanics. Quantum discord is also there, which is studied, and other types of correlations are also there. Non-classical correlations are there. So for all these correlations, quantum coherence is actually very important. But there is a difference between quantum coherence and quantum entanglement. For quantum entanglement or quantum correlations, any type of quantum correlations, minimum number of parties must be 2. But in quantum coherence, a single party is enough, because in quantum system, a particle is expressed in alpha cat 0 plus beta cat 1 way. So we also can get coherence from this single qubit system. But for in non-classical correlations, we need to have 2 parties to be involved. Okay, so go to the next slide, slide number 8. Quantum coherence and entanglement are arguably the most significant phenomenon in quantum mechanics that marks the departure from classical mechanics. Entanglement has no classical analog, but unlike this, coherence is a familiar event in optics. Now, those who are actually doing research in quantum optics, they know this very well, that quantum coherence, this particular word, I'm not talking about quantum coherence. Coherence is something which is not connected entirely to, which was initially not connected entirely to quantum mechanics itself. In these two famous paper, one by ECG Sudarshan and another by I can say the pioneering papers, and another by R.J. Glauber. They actually did works on coherent and incoherent states in red. Glauber worked with coherent and incoherent states in the for radiation field, and the ECG Sudarshan was the first person to study on coherence from India, actually. So these two papers are very phenomenal paper, and the people who actually work in quantum, works with optics, they know that the existence of these two papers very well. But coherence was actually, everything which was classical in 20th century, now it is in 21st century that has become non-classical. Quantum mechanics, quantum fluid mechanics, quantum dots, everything. So the coherence, this quantum optics, the common thing that was previously there in classical physics, now it has been shifted to quantum physics, and now it has become, we study the quantum coherence. So this is these are the two papers that I wanted to show to you. Those who are interested, they can study these two papers. They are available free. Go to the next slide. My friend Professor Monirul Ali has also joined. Thank you. Yeah. Now, for measuring quantum coherence, we actually have several measures. Okay, so we can measure the quantum coherence by a quantity called L1 norm, and another is relative entropy of coherence. In our paper, we have used the formula 1, that is L1 norm. In L1 norm, what we do, we have a quantum state and we try to figure out the density matrix of the state. And as you can see in the formula written on the right hand side, we add the absolute values of the matrix elements, not the diagonal elements, but the off diagonal elements. We actually add them up, and that will give us the L1 norm of the coherence. And the rho ij, by rho ij, we actually denote the matrix elements of the density matrix. While in equation 2, we can see that another formula is there, which is called the relative entropy of coherence. And this is actually the formula given by is a optimization technique, which is the optimization is taken over all possible separable states, and we calculate the von Neumann entropy of rho with respect to the separable state sigma. And go to the next slide. Next slide, slide number 10. Yeah, and this CR rho, this, yeah, no problem, no problem, no problem. Now, this in the previous page, the formula that was written for relative entropy of coherence, that has a computational form also. This computational form is shown in equation number 3, where rho d is the dephased state in the reference basis I. That is the state obtained by deleting all the off-diagonal entries. Okay, so what we do actually, we get a quantum state, we generate the density matrix of the system, which we denote by rho. We calculate the von Neumann entropy of the system, and then from the density matrix, we eliminate all the off-diagonal terms. We get the matrix rho d, and then we calculate the von Neumann entropy, and we also subsequently we find the difference between the two von Neumann entropies, which is the relative entropy of entanglement. My collaborator and mentor, Professor Monirul Ali, he is very good in calculating relative entropy of coherence. They do this with the help of mathematical programs, numerical calculations. But L1 norm of coherence is also very easy to apply. So in those days, when we were working in this particular arena, my colleague Anushka Bhattacharya was new to this particular subject, so I didn't put much pressure on her mind. So I told her that you just work with L1 norm of coherence because it's easy to calculate. So that is the reason. But L1 norm of coherence and relative entropy of coherence both give you the same result. Go to the next slide. And any coherence measure, be it L1 norm and or relative entropy of coherence, they must actually satisfy some of the properties, like the properties that I have bulleted over here. One property is that the measure must vanish on the set of incoherent states. The measure should not increase under incoherent operations. There must be monotonicity. Monotonicity of the measure must be preserved, and the measure must be completely positive and trace preserving. And measure must show decrease in coherence under mixing. All these are very technical terms. I know there are students who are actually listening to this particular talk from YouTube live. So until unless I'll say to them, until unless you are working with quantum information science or quantum mechanics, I think these bulleted points will not be understood by you properly, because for these you have to have some knowledge about linear algebra, that what is completely positive map, what is trace preserving map, why trace is important. So I have just noted down these particular points to let you know that these properties must be satisfied by any measure, which is any measure that you use to calculate the coherence of the system. So relative entropy of coherence and L1 norm of coherence both actually satisfy all these properties. So you can choose. So that is the game. You can choose between any two of them, whichever you can feel comfortable with. So we chose L1 norm to calculate the coherence of the system. Go to slide number 12. Now, another important fact that I was telling from at the beginning of my slide, that the right choice of basis to be used to estimate the coherence is the separable basis. So when we were actually, I was thinking of the problem, and when I was thinking of the problem and I was learning coherence and at that time, so I actually faced some difficulties, and with that difficulty, I actually first approached Professor Biplab Ghosh, and I asked him that a problem has arisen. I have some difficulties in understanding what is coherence and how I'm getting different values for measure by applying two different measures on the quantum state. So can you shed light on this? So he tried to figure out the things, and then as you know that gradually, ultimately many people came in, like Professor Manurul Ali got into the system, and we also kept on discussing, and we are trying to figure out. We applied these things, this particular we kept on discussing about this particular thing by considering many quantum states, many possible different quantum states. And Professor Anushri Bhattacharya, she was also doing hard works on that, writing programs and doing checking numerically. And then we sought some expert opinion, and we approached Professor Chandrasekhar Radhakrishnan, who was collaborator of Professor Manurul Ali from his Taiwan days. And then when he came into the picture, he's an expert of quantum coherence. So he told us that that we need to have this coherence is actually basis dependent. Coherence measure is basis dependent, and therefore you have to be very careful about what basis you are choosing. At that very moment, it clicked in all of our mind that the quantum information processing paper by Adhikari, etc., and all that they showed in this, I showed you in the previous slide, that paper was lacking something in it, because they actually focused on computational basis. They didn't focus on every basis. So we came to know about the fact that we would be able to give some counter example, and luckily everything materialized properly, and we, five of us, we started working on that, and the outcome is that world scientific paper on which I'm giving talk right now. Go to the next slide, 13. So the goal of the paper was, how does coherence affect the fidelity of teleportation of certain mixed states, how teleportation fidelity of mixed states behave as per the variation of coherence and concurrence. These words, teleportation fidelity, mixed states, concurrence, have been marked blue. Also, how do mixed states behave with respect to Bell's inequality? Bell's inequality has been marked blue, because in the upcoming slides I am going to explain all of these things, because these need to be explained. So therefore these terms, new terms, teleportation fidelity, mixed states, concurrence, Bell's inequality, new terms for the students who are listening. So that's why I have marked these terms over here. I'm going to explain them gradually. Go to slide number 14. Now, first of all, let me talk about quantum teleportation. Quantum teleportation, this particular picture has become very famous because, I'm a movie freak. I always watch Hollywood movies, and this movie came out in the year 1978, probably, or 1979. The movie is The Fly. And this movie was, you can see in the picture that there is a pod. This type of pod, you enter into this pod, and these two different types of pods are connected by wire optical fibers side by side, and you enter into the pod, and the protagonist does some mechanism, and you disappeared from the first pod and you reappeared in the second pod. So that was a science fiction. Actually, it's a classical teleportation they were talking about. But quantum teleportation is not like that. Whoever actually came to do research in quantum information science, they were very much extremely I mean become enthusiastic with the quantum teleportation. But the enthusiasm, I also became enthusiastic when I heard the term quantum teleportation, because I tried to connect quantum teleportation with the movie The Fly. And my research guide, Professor Archan Mojumdar, he actually was able to break down my enthusiasm, because I know that this is not completely what was happening in this science fiction movie, because it is a reality, and in reality quantum teleportation is not entirely quantum. So some parts of some classical parts is actually maintained, should be maintained. Otherwise, Einstein's causality, things moving faster than light, that would be violated. Relativity would be questioned. So some classical part is also has to be maintained. So it's not totally quantum. And to quantify whether a given state is actually able to do, whether a given state is actually be able to be used as quantum channel for performing quantum teleportation, there is a term called teleportation fidelity, which gives you the non-classicality of the quantum channel. And the theory goes like that: if the state has to be if the state has to be useful in quantum teleportation as a quantum teleportation channel, its teleportation fidelity has to exceed the value of classical fidelity of 2/3, which I have marked as red. And this paper you can find in the journal Physical Review Letter 72 by Sando Popescu. And one of my mentors, I respected mentors, Professor Dipankar Home, in the year 2016, they showed that the classical teleportation fidelity, if exceeded, the classical teleportation fidelity value 2/3, if exceeded, and then it is we can say that okay, the channel is useful as for quantum teleportation, but it is not actually non-local, totally non-local. It is, you can say it is non-classical. But they showed that if the teleportation fidelity exceeds 0.9, then you can say that the system is totally non-local. So you can get this particular very interesting paper by Professor Dipankar Home and his team in the archive, which I have mentioned in the footnote. Please go to slide number 15. Here I have given a schematic of the quantum teleportation protocol, which I am trying to explain very briefly. That you can see that the person Alice is there present, and she will be having some sort of unknown state with her. And this unknown state will be in the form of qubit, which I have marked on the right hand side above. You can see Psi1, A0 plus B1, mod A square plus mod B square must be equal to 1. Probably this is missing. Anyways, so this is the mathematical abstraction of representing a qubit. The Alice will hold this qubit, and Alice cannot measure this qubit, because if he tries to measure, the Schrodinger cat-like thing will happen. The classic quantumness will break down, and classically she will get either 0 or 1. So she cannot measure her state, but she wants to send this particular state to Bob. She wants to teleport the state to Bob. So she will have to have some sort of entangled channel with Bob, which the Bob and Alice can prepare by themselves, or some third party can prepare the entangled state for them. And then Alice will club this particular single qubit with the entangled state, and will do some sort of mechanism, mathematical mechanisms, which I'm not going to explain over here. And then she, on the side of Bob, the exact state can be regenerated, or in some other form. Now Alice will tell Bob that Alice will apply von Neumann measurement on her part of qubits and joint von Neumann measurements on her part of qubit, and she will telephone or email Bob that this is my measurement result, and Bob will say, okay, fine, then if it is your measurement result, let me apply the unitary operator on the state that I have obtained on the basis of, and it is predetermined. So if Alice gets this measurement result, then Bob is going to apply that measurement operator. Alice gets this measurement result, Bob gets to apply another measurement operator. In this way, Alice will be able to teleport the quantum state to Bob, and in the due process, the state is totally unknown to Alice, and lastly, at the end of the process, the state will disappear from Alice's end and reappear at Bob's end. Now, that is, people think that this is the science fiction, but this is not a science fiction, because if it were a science fiction, there should not be any telephone call or emailing. Since there is a telephone call, nothing is moving faster than light, so Einstein lives. Okay, so, and you can see a box like thing over there circling to circle, cutting one another. That's called entangled state, which is actually the channel that Alice and Bob will be sharing. In Bennett's, the quantum teleportation was actually it actually was I mean, the father of quantum teleportation was Charles H. Bennett, and if you read the original paper of Charles H. Bennett, you can see that they applied, he applied the singlet state, which is actually 0, 1, minus 1, 0, divided by √2, but you know that there are 4 possible Bell states are there. I'm going to show you in this next slide, but any of the states can be used. Any of the possible Bell states can be used as an entangled state for doing this quantum teleportation from Alice to Bob. Now, recently I had a talk with Professor Dipankar Home, and he was a very funny person sometimes, and he says that, okay, you know, Shobik, that Alice, the word Alice was actually was used very, cleverly. You can relate this term Alice to Alice in Wonderland, because quantum mechanics is kind of Wonderland to all of us. Okay, but you cannot find anything similar to Alice and Bob in our Indian system. So one of the friends of Professor Dipankar Home, he suggested Hada and Bodha. Hada is sending this unknown state to Bodha. So the Professor Home is not liking this very much, and he said that, okay, in Indian system is a patriarchal system, so we do not have any important female character to whom who can replace Alice in this quantum mechanics research. So it is his version, and therefore I liked his version. I liked him very much, and so we still use Alice and Bob. This is a trend. Okay, so that's why I'm using Alice and Bob here also. Go to slide number 16. And you see that, as I mentioned, that these are called the Bell states. These Bell states, any of these 2-qubit systems, okay, they are a pure entangled state, maximally pure entangled states. Any of these states can be used as entangled channel between Alice and Bob, which will help Alice to teleport her unknown qubit to Bob. So the 4th channel, which is denoted by var phi minus 1 by √2, 0, 1, minus 1, 0. The 4th one actually was used in Charles H. Bennett's original paper, which I have mentioned in the footnote, 1993 paper. You can read this paper. It's very interesting. And for the understanding of Bell state, you can go, you can study the following paper, which is by J.S. Bell. This paper is also available free. You don't have to subscribe any journal for this. Go to the next slide, slide 17. And now let me talk about the quantum entanglement, which is another manifestation of the superposition principle. The quantum entanglement means the more intrinsic quantum mechanical sense in which quantum states can embody vastly more information than its classical counterparts. So equation number 5, there are 2 parties, Alice and Bob, and if And you know that quantum mechanics, actually previously known as matrix mechanics by Heisenberg, later it became quantum mechanics. So since there is a matrix involved, so there is linear algebra involved, and since there is a linear algebra involved, so there is a vector space involved, and the vector space that we play with is called the Hilbert space by David Hilbert. And quantum mechanics is a kind of physics which is actually being played in the home of Hilbert space. So HA is a Hilbert space of the cis Alice, home of the Alice, and HB is the Hilbert space home of Bob. And from that, these two homes, they select their basis I, which I represented by IA and JB over here. And if a particular, their joint system can be represented as equation 5, which is a tensor product. You can see the symbol between IA and JB in equation 5. It is called the tensor product. If, in any mathematical software, if you use, sometimes it is also called Kronecker product. So it's a kind of matrix multiplication, a different type of matrix multiplication. It is actually used to club two systems. So if there are two systems, if you want to club them, so the mathematics is you take the tensor product and the system becomes large. So if the Alice and Bob's joint system can be written in this particular form, then we'll not say that they are entangled. But if we cannot express the joint system of Alice and Bob as equation 5, we'll say that the system is entangled. Okay, so the definition is given like this, not like this. Directly, it is not given. In this particular slide, the definition is given like a roundabout. Okay, so this is called the entangled state. If it is not, if the state cannot be expressed as equation number 5. Go to slide number 18. And now the mixed entangled state. The a mixed state of quantum systems consisting of various subsystems is supposed to represent entanglement if it is inseparable. And you see that in equation number 6, the rho I, the term rho I, A1 is a kind of, you can say, a pure state. Rho I A2 is a kind of pure state. And now if you take a convex combination of all these pure states together with summation pi equal to 1, condition and pi, these are probabilities, actually probability amplitudes actually. So this type of, if a particular density matrix can be expressed mathematically as in given in equation number 6, then we say that such type of system is mixed entangled state. The actual meaning of mixed entanglement is that your system is actually subjected to noise. I mean, when we, if we think classically, when we telephone maximum time when I call Surojit sir and his voice cracks and he said, okay, so Shovik, WhatsApp a call koro. So this, the noise that actually appears is the disturbance. So here, I'm telling something and it is getting through the line and is reaching to the receiver of the Surojit sir phone. Sometimes it gets disturbed due to the noise in the system. So how we represent the noisy states in quantum system is by the mathematical equation which is represented as equation number 6, and such type of state is called the mixed entangled state. In our research work, in this research work, we have worked with mixed entangled state. Go to the slide number 19. And now, previously we actually talked about the measure of coherence. Now we are talking about the measure of entanglement. There are so many measures of entanglement which you can apply and which I have not mentioned over here. The relevant one, which is the measure which is relevant to our work, I have here in equation number 7, which is known as concurrence. And what we do actually, we take a state, we find the density matrix, we find the density matrix of the system, and then we find the complex conjugate of the density matrix of the system. Complex conjugate means you can represent, I am representing the complex conjugate by rho star. Atanu, you can show your cursor in equation number 8, this rho star. Yeah, rho star. No, this is rho tilde, rho star. Yeah. we actually take the complex conjugate of the matrix elements and then we take the transpose. So if you have 0 I minus 0, so we take the complex conjugate which becomes 0 I and minus I 0 and take the transpose of the matrix, and then on the left hand side we have sigma y tensor sigma y and sigma y tensor sigma y. These are sigma y is only one of the Pauli spin matrices, so we take the tensor product of these two, and from both the sides we multiply the tensor products, we multiply rho star by the tensor products, and the matrix. Yeah, sure. Yes. Any questions?
Yeah. I have one small question. That is the equation 8, what you have defined. So is it defined or it is coming from some
It is
from some
defined.
derivation or so?
It is coming from some derivation which is mentioned in the paper 1998. It is not the derived. It has been derived in the paper 19 of Physical Review letter 1998 by Wouters. The formula is by Wouters, and the entire derivation is shown over there.
Okay. This is for the mixed states.
Yeah, you can apply this. The concurrence can be applied in pure as well as for mixed states, both. For bipartite system, it is mainly applicable. For
But the thing,
higher dimensional system, it is not
yeah.
applicable.
But the thing is that you have earlier various measure of concurrence, not concurrence. There is the coherence.
Coherence.
What you have defined, it is different, right?
Different.
So pattern of mixing,
yeah,
amongst the various states.
Yes.
It may be different.
Different.
So if we define by the Wouters method, if we derive it like this, this concurrence, this is it a unique definition of this concurrence?
Yes.
Or not, or any particular method, particular bipartite system, specific bipartite systems, for which it is defined.
No, this particular what you are asking, I have understood that this particular formula, equation number 7 and equation number 8, is actually for any bipartite system, be it pure or be it mixed. But this particular formula actually fails if you go to higher dimensional system or a multipartite system. Concurrence, this measure will not work. This measure is very fine with
yeah, if you go to the 3-particle system, then
it will not work. It will not work. And obviously there is a thing that concurrence is.
No, I am not referring 3-party system. So the 3-party system, I am referring 2-party system. What I am telling that suppose if your this coherence.
Coherence. No. Interesting question. Okay. Maybe I have not understood the question properly. So you are asking about coherence, right?
Yeah. That is for mixed pattern. What he is referring in Wouters paper or here in the derivation of this equation number 8 or the concurrence 7. Okay, so it is following for some mixed state, right? So mixed state.
So he is calculating the entanglement.
Is it of same class, same category? There is mixed 1, mixed 2, mixed different categories of mixed states. Maybe they are for which different coherence number.
No, coherence and entanglement are not exactly the same in technically.
No, that's right. Okay.
Okay, actually, this coherence, and as I told you that earlier in my slide, that coherence can exist in a single qubit, but for concurrence you need at least two qubits. So the things by the way of mixing, there is no kind of such thing like mixing dependent.
Okay, if you allow, Sovik, maybe
sure. You can share
very quickly. Yes. I try to because I am trying to understand Professor Suraj's question. So if I understood properly, when we calculate the coherence, then we actually first have to identify what are incoherent states. Okay, then we calculate the distance of my state from those incoherent state, and then we actually properly calculate a distance measure, and then we optimize. Then in that process we get the coherence. So coherence is distance from incoherent state. Now entanglement, when we calculate, in Utter's paper, I do not remember completely. So it has to do with the entanglement of formation.
Yes.
Yeah.
Entanglement formation. From entanglement of formation, they have derived concurrence paper, concurrence formula.
Yeah.
It's actually a function of, the h of c. This function is there.
Yeah, Utter and Hill. Dear Sobik, Utter and Hill.
Utter and Hill. Utter and Hill.
Entanglement
Hill.
formation
No,
is
my,
small
my,
because
my, yeah,
directly
my,
proportional to concurrence.
can I redefine my queries? It is
Yeah,
not
yeah, sure.
query. Yeah. So suppose you have a mixed state, right? So is it mixed states? Is it a unique type of mixed state? Suppose if you have a mixed state, right? Suppose category 1, it may be category 2, it may be category 3, because take the example of coherence. Coherence, obviously, it is totally different from entanglement. That I understand. Okay. But
Maybe just one point I want to add, Professor Surajit. Actually, you can calculate entanglement also in this using this distance measure. So for that, we have to identify the separable state, and then we actually cleverly choose some distance measure. That is, my state is how far is from the separable state. I mean, now I am asking this question. Earlier I was asking what is the distance of my state from all the incoherent state when I was talking about the coherence. Now when I will be talking about entanglement, I am asking this. I have a state rho, and now I am asking this state how far it is from these separable states. Now then the optimization will be on over the all the separable state. Earlier it was the optimization was over the incoherent state.
Incoherent states.
Exactly.
Obviously, you will end up with different.
So let me say. So in a nutshell,
Surajit,
total quantumness of systems of any system actually, but entanglement formation measure the non-local correlation between two or more party system actually.
Surajit, let him proceed.
Yeah, please proceed.
Yeah.
Okay.
It's nice discussion. Okay, fine, no problem. So that is the formula of concurrence of the concurrence by which we measured entanglement in our paper. Go to the next slide. Is slide number 20. We can always come back later in the question answer session. And another thing that we actually measured in our paper is called the mixedness, for which we applied the measure called linear entropy. Von Neumann entropy measure is also there, which we could apply, but this particular measure has been applied because it is applicable to any system. It's applicable to any system, be it two-dimensional or higher dimensional system. So as you can see in the formula, equation number 9, we have d by d minus 1 minus trace of rho square. So d means the dimension of the system, and the linear entropy varies from 0 to 1. So for the simplicity of this particular formula, we used this particular linear entropy for the measure of mixedness. The details of the paper is mentioned below in the footnote. Go to the slide number 21. And now in that paper, to counter the statement of quantum information processing paper, where the authors mentioned that the L1 norm is always greater than or equal to concurrence, and where they actually didn't put emphasis on the basis on which they are measuring, we set the counter examples, like we designed these mixed states which are represented in equation number 10 and equation number 11. In these states, the specialty of these states, you can see that they are actually both of these states we have represented equation number 10 as class 1 states and equation number 11 as class 2 states. And in these two states, they are the convex combination of the Bell basis as well as the separable basis. So if I can take into consideration row 1, so we can say that it is a convex combination of 5 plus and 5 plus and 0 and 0. So there are in total 16 possible cases, because you can see that I have mentioned, I have denoted them by plus minus sign. And then another 16 possible cases will emerge, which you can get by combining by taking the convex combination of the Bell basis with 0001 and 0011 like this. So many possible mixed states can be constructed in this particular manner. But here in this paper, we have constructed the states, class 1 states in equation 10 and class 2 states in equation 11. Go to slide number 22. And as I have already mentioned this in the previous slide, that we are going to say the equation number 10 is class 1 and equation number 2 is class 2. And since in our study, one of the measures that we are actually using is coherence, so we need some basis. So here we are taking two bases actually represented by B1. In B1, we're taking the computational basis, but which are also called incoherent basis, or separable basis. There are several names are there. So these are called 0001, 1011 are the basis elements. And in B2, we have the entangled basis, which are represented by phi plus, phi minus, psi plus, psi minus. So these two, on the basis of the two bases, based upon these two bases, we are going to calculate the coherence actually in our paper. Go to the next slide, number 23. And then when we applied these two bases, we first of all, we calculated in computational basis, using the computational basis, we found the coherence of the class 1 states as we found the concurrence of the class 1 states using and we found the mixedness of the class 1 states as well as class 2 states, which are represented in equation number 12 and 13. And you can see that both the class 1 states and class 2 states, their coherence, their concurrence, their mixedness, all are dependent upon the state parameter P1 and P2. So if you vary, they are they are also varying. Okay, go to slide number 24. You remember this figure. I can ask Otonu to come back to this particular figure later after when I will proceed. You'll come back to slide number 24 once again after some time. So you can see that once we did the calculation in computational basis, we found that we varied the parameter P1 and P2 from 0 to 1, and consequently the coherence and the concurrence kept on changing. So class 1, the left hand side figure is for the class 1 states and the right hand side figure is for the class 2 states. And you can see that in the red line that is being shown in the left hand side is the coherence. So with the increase in the value of parameter P from P1 from 0 to 1 and for P2 from 0 to 1, the coherence is decreasing gradually from 1 to 0, while concurrence is increasing from 0 to 1. So they are inversely proportional to one another. And the mixedness of the system, which is denoted by L rho, is achieving the highest value, the model value for P1 equal to 0.5, which is given by L rho. But as if you compare the two class of states, I mean class 1 and class 2, you can see that although there is no change in the movement of coherence and concurrence for the two class of states, but the mixedness is actually changing. The mixedness for the class 2 states is higher than that of class 1 states. So you can see the figure, but the model value of the mixedness of the linear entropy is achieved at 0.5. Go to the next slide. And I have also this, what in this particular slide is not that very important. I have already told the observation of what we actually got in this particular figures. So the students who are actually attending, if they get this particular slide, they can read it out from here, that what we are actually observing in the previous slide number 24. Go to next slide number 26. And then we applied the Bell basis to measure the coherence. But now, Atanu, you can show the slide number 24 once again. Now you see the difference. In slide number 24, there is a red line, which is showing you the coherence of the system, CL1, CL row. But in slide number 26, there is no red line. Now, as if it is showing that there is coherence and concurrence, both of them are merging onto one another. We are not actually seeing any trace of coherence over there. We started with this actually. When I started working on this particular paper alone, I started with this, and that is the main point. That is the main issue which I called Dr. Biplav Ghosh, and I started discussing what is happening. Am I doing wrong, or is something there fishy is happening over there? And then Professor Moinul came and he helped, and then Chandrasekhar Radhakrishnan, he actually solved this puzzle. And so you see, the main important part is that so no red line is being shown over here, and you cannot distinguish between coherence and concurrence. What is happening? The Bell basis is itself an entangled basis, so it is catching the coherence inside it. So it is not showing, it is not exposing the coherence. If you calculate the thing in using the Bell basis, it is not exposing. But you have to shift to separable basis, a computational basis. Now, I'm not telling that in quantum information processing paper by that paper where they mentioned, I mentioned in the beginning of the slide, they didn't do anything wrong. Their statement that L1 norm is greater than or equal to the concurrence of the for any two qubit system, statement was wrong, proof was wrong. Statement was right, proof was right, but the only thing that they forgot to mention is the basis. They forgot to mention that there is basis dependent quantity. So if I choose this basis on with respect to that basis, this formula is holding out. So this is happening. So if you have to be very careful when you calculate coherence, which basis you are taking. Now, one precautionary measure that you have to take, and we actually face this difficulty while writing this paper, that suppose you are, for a particular class of states, you are calculating coherence using a basis 1, computational basis, and you are calculating concurrence also, then you cannot shift to Bell basis. If you are doing the calculation for all the all the calculations for a particular basis, you have to stick to the basis. Otherwise, the comparison will not be correct. So if you want to calculate the concurrence, coherence, mixedness with the help of this computational basis, do it in computational basis. If you want to do it using Bell basis, do it in Bell basis. So you have to be very careful about this particular thing. So go to slide number 27. And here also the observations that I have already discussed in the previous slide has been made. So I'm skipping this slide. Go to 28. So this particular slide is actually important. Why is there a difference between representations in computational Bell basis? So I'm reading this out because it is directly from our paper. The computational basis is a separable basis in the sense that the 2 qubit basis states can be written as a tensor product of the single qubit basis states. Hence, these basis states do not contain any type of quantum correlations or coherence within them. Meanwhile, if we look at the Bell basis, the 2 qubit basis states are the entangled states, and they cannot be written as tensor product of the individual basis states. Hence, these basis states inherently contain entanglement and coherence within them. The behavior of mixedness, however, in the two representations is the same. So sometimes it is very good to read directly from the slide, because otherwise, if something I miss, then the misinformation will be conveyed. So this is the main essence of this particular paper. Go to slide number 29. And later, Professor Chandrasekhar Radhakrishnan, he told us that they, in the year 2019, they actually did a studied, and they actually figured out a particular measure on which is actually basis independent measure called for quantum coherence, and that paper has been published in 2019 in the Journal of Annals of Physics. So we didn't use this particular formula yet, but this is a kind of measure which is basis independent. But the L1 norm and this relative entropy of coherence, they're all basis dependent measures. Okay, so that's why I'm actually, those who are interested, they can study this particular paper and find it out what is it actually. Go to slide number 30. And here I have written about the mixedness, the things that I found as the mixedness of the constructed state. So we have found from the plots of the two class of states, the maximal value of mixedness is class 1 states is lower than that of class 2 states. And this is because the class 1 states have only 2 diagonal elements, whereas the class 2 states have 3 diagonal elements. And mixedness is the distance to the maximally mixed state I by 4, where I is the identity matrix which has 4 diagonal elements. Now this can only be understood, this is a very technical part, this can only be understood if you just do the calculation by your own and you just explicitly write what you have got, and you can only figure out what has been written over there. Okay, so the maximally mixed state is actually given by I by 4, and the thing that already I have mentioned in the previous figure, that the mixedness of the system of class 2 states is greater than that of class 1 states. That has been mentioned in this particular slide, our observation. Go to slide number 31. Now, teleportation fidelity. Teleportation fidelity provides us a different notion of quantum inseparability. In this method, the information in given quantum state is separated into classical information and quantum or non-classical information, I must say. What teleportation actually is has already been explained to you by schematics in my earlier slide, how it works out. So I'm not explaining it right now. That thing has already been mentioned. Go to slide number 32. For measuring teleportation fidelity, which is actually quantifiable, as I told you that once you want to find out that a particular quantum state is useful as teleportation channel, then the teleportation fidelity must exceed the classical teleportation fidelity of 2/3. So if the classical limit is exceeded, then our job is done actually. So there, teleportation fidelity is quantifiable, and this formula that we use actually is given in equation number 15. I have written many things over here. You can see what n row, how its elements actually calculated. The elements are represented, the matrix are of capital T are represented in 16 by equation number 16. But if I want to say in a single line how do we calculate this n row, I can say it is the sum of the singular values of the matrix row, matrix tree, singular values of the matrix tree, because you know that in linear algebra, the singular values of the operator T is actually the eigenvalues of the matrix T dagger T. So the root over of the singular values actually. So in this way, we construct by using equation number 16, we can construct the operator, the matrix capital T. We find the eigenvalues or singular values. We take the square root and sum of these singular values, and we substitute these value in equation number 15. We get teleportation fidelity, and we say that the state is useful for teleportation if the quantity n row is greater than 1, which has been proved in the paper by Horodoki, etc., and all in the year 1996. Okay, so if n row is greater than 1, the state is useful for teleportation. Go to slide number 33. And then we applied this formula to our states. We found for class 1 states, the teleportation fidelity is given by equation number 17, and teleportation fidelity of class 2 states is given by equation number 18, and the teleportation fidelities are also parameter dependent, and they are useful. And we found that the class 1 states are for the class 1 states are useful for teleportation, as useful as teleportation channel for all the parameter values from 0 to 1, as n rho I is greater than 1 for all p1 lying between 0 and 1. Whereas for class 2 states, we found that the states are useful for teleportation when the parameter values are lying between 0.5 and 1. So not all entangled states. The take away home message is that all entangled states are not useful as teleportation channel. There's some states are there who may not be useful as teleportation channel. So go to the next slide, 34. So we actually mentioned here in details that as for class 2 states, it is observed that for P2 lying between 0 and half, the teleportation fidelity of the states is less than classical teleportation fidelity and not suitable for quantum teleportation, and so on and so on, which has already been mentioned. The only you have to keep in mind that if you find that any particular state is entangled, you cannot immediately declare that it would be useful for teleportation channel. You have to do some more calculations on that. 35. Slide. Yeah. And now there comes the CHS ability. As I told that I also studied here that for our constructed state, what is the condition of the violation of Bell's CHS inequality. Now this talk will remain incomplete. Would have been incomplete other if I do not mention their names and their papers over here, because as I already told you, the study was Einstein's birthday, and to dedicate this talk to him, my talk is also dedicated to Compton, whose death anniversary is today. So this paper came out in the year 1935, and can quantum mechanical description of physical reality be considered complete? Einstein and his collaborators Boris Podolsky and Rosen, they wrote they put a question mark on the physics of quantum, and they said that it is not compatible with what we see in the realistic scenario. It's actually incomplete. Something is missing, and we have to find out the missing part. And in the year 1964, Professor John Bell of CERN, he actually gave us a phenomenal paper on quantum mechanics, and the paper is titled as On the Einstein-Podolsky-Rosen Paradox. There he didn't discuss about anything about quantum. He discussed about, he put the question of Einstein, he gave it a mathematical form. He gave the question posed by Einstein a mathematical form, and he said that the correlation the Einstein and his team is talking about, if the correlation has to work out, then my inequality, his Bell's inequality, this inequality has to be satisfied. Then he stopped. Okay, so then the game started. You see the gap between 1935 to 1964. In between this gap, nothing was. I mean, quantum physics was not dead, but was questionable. And the Niels Bohr and Einstein kept on fighting with Bohr's Einstein debate. There are many good books have been written on that debate. Okay, so debates